So we're going to talk about the fourth quantum number called the spin quantum number and some rules, the Aufbau principle, the Pauli exclusion rule, and Hund Rule, and how these lead to what are called electron configurations. So the fourth quantum number called the spin quantum number comes about because electrons act as if they're this little sphere of spinning electric charge. They're not. They're waves is what they are, although they can act like particles, wave-particle duality. But they sure behave as if they look like this. And what does it mean to behave like that? Well, physics tells us that anytime you have an electric charge that spins, it creates a magnetic field perpendicular to its direction of spin. And what does that mean to create a magnetic field? It means that if you put a magnet by this, it's going to feel that magnet. If you bring a north pole of a magnet up to the north pole of this magnet, it's going to push it away. North poles repel, or south pole to south, it would repel. If you bring a south pole up to the north pole, it's going to attract it. And electrons display this behavior, no doubt. And the rule for what this fourth quantum number, which is called m sub s, is that it can have only one of two values, plus a half or minus a half. For us, it's not going to matter at all which one it is, or that the value is 1/2. The only thing that matters to us is that there are two values, and only two, that m sub s can have. You'll see why in a minute when we talk about the Pauli exclusion principle. Right, so we have this fourth rule. Now notice the difference between this quantum number and the first three, n, l, and m sub l, is that n, l, and m sub l describe the region of space, or an orbital, a shell, a subshell, and an orbital, where an electron can be. M sub s talks specifically about the electron itself. Okay, so next, there's this principle called the Aufbau principle that says that electrons in an atom will always occupy the lowest energy orbital that has room for them. Okay, and so we have to know, relative orders of orbitals, right? So in general, okay, as the shell or the principal quantum number increases, that increases the energy. We've seen that before. Now within any shell, say n equals 1, 2, 3, 4, what have you, say n equals 4, within that shell, an S subshell will be lower in energy than a P subshell, which is lower in energy than a D subshell, which is lower in energy than an F subshell. That is if there is more than one electron in that atom, which most of the atoms are going to be like that. So that's the Aufbau principle. Higher N means higher energy within a shell. S is less than P, which is less than D, is less than F. So now if it's a hydrogen or a hydrogen-like atom, then the only thing that determines relative energies of orbitals is N, the shell, the principal quantum number. N equals 1 is lower than N equals 2, which is lower than 3 or 4. And at N equals 2 for a hydrogen or hydrogen-like atom, that is only one electron. 2s and 2p orbitals are degenerate, that is, they're at the same energy level. And same at 3, 3s, 3p, and 3d, and so on. However, as in almost all the atoms we're going to deal with, there's more than one electron. These degeneracies split. In other words, it looks like this. At the n equals 2 subshell, there's a 2s and the 2 n equals 2 shell. There's the 2s and the 2p subshells. Now remember, the s is lower than the p, so it looks something like this. Although the 3p orbitals in the p subshell are degenerate. N equals 3, 3s is less than 3p is less than 3d. The p's are degenerate, the d's are degenerate. Now notice this little slippage here. Notice how the 4s kind of slipped in underneath the 3d. We're going to talk about why that is in the next module, but for now it's just good to remember that an electron in a 4s subshell is lower in energy than an electron in a 3d subshell. And the importance of that is that the Aufbau principle tells us that when we're putting electrons into atoms, which is what we're going to do here, they're going to go into the 4s before they go into a 3d subshell. Okay, the next rule, the Pauli exclusion principle, what it says is that in any atom, no two electrons can have all four quantum numbers identical. That is n, l, m sub l, and m sub s. As a practical matter, what this ends up meaning for us is that you can't have you can't have any more than 2 electrons in any single orbital. And if they are in the same orbital, they have to have opposite spins. So let's imagine we have 2 electrons. So they both have, I don't know, to pick some quantum numbers. Let's say n is equal to 3. L is equal to 1. I don't know, pick a value from M spell, doesn't matter, equals, negative 1, let's say. Now we could have 2 electrons in the same atom that have all these 3 quantum numbers the same, but the 4th quantum number has to be different. For 1 electron, it's going to be plus a half, or spin up is what we say. If there's a 2nd electron in that atom that has n equals to 3, L equal to 1, L equal to L, yeah, that would be true. L equal to 1, and M sub L equal to minus 1, then M sub S has to be equal to minus 1/2. And there's no other possibility. That's the most electrons we can fit into this orbital. This would be a 3p orbital, one of the 3p orbitals. Next rule, Hund's rule, says that when you're putting electrons into degenerate orbitals, 1 electron has to go into each degenerate orbital before you pair them up. And whichever spin that first electron has, the next ones have to have, that go into the other orbitals, have to have that same spin until you start pairing them up. Let's go back here a minute and look at some degenerate orbitals. So let's say the 2p, right? Let's say we're putting electrons into a 2p subshell. What Hund's rule says is that we have to put an electron into here, and then whatever spin this is, so this is how we represent electrons with arrows, right? Because they can point up or down. So because I randomly put this first arrow or electron with the spin down, the next one has to go into another empty orbital with a spin down, and if we have another one, that also has to have spin down, goes into the next empty orbital, and only until we get to the 4th electron do we start pairing them up with the opposite spin. That's what Hund's rule says. All right, so applying these rules allows us to get what are called electron configurations. So we're going to look at some of these guys. The idea is that first of all, we're only doing neutral atoms. In other words, no overall electric charge, meaning that we have the same number of protons as electrons, or vice versa. So in a hydrogen atom, there's 1 proton. So in neutral hydrogen, there's 1 electron. It's going to go into the lowest energy orbital, which is the 1s, and it's either going to be spin up or spin down. There's still room for 1 more electron in there, so when we get to the next atom, 2 protons, the 2nd electron goes in there, but it has to have the opposite spin. Right down here, this is what we call electron configurations, 1s1. The 1 in front tells us the N. The S, the letter, tells us the subshell, and the superscript tells us the number of electrons in that subshell. So 1s1 means there's 1 electron in a 1s subshell. Helium's 1s2, 2 electrons in the 1s subshell. The next element, as we're going up in atomic number, is lithium, 3 protons. Neutral lithium has 3 electrons. Now with that 3rd electron, the 1s subshell is full, so we go to the next highest energy subshell, which is the 2s, and put that 1 electron in there. And then beryllium, and so on. Now let's look at carbon. Carbon is where we hit Hund's rule. So carbon has 6 electrons. First 2 go in the 1s subshell, 1s2. The second 2 go in the 2s subshell, 2s2. Everything's full there. The next electron goes into the 2p subshell. And then the last electron, Hund's rule says, has to go into an empty 2p orbital with this whatever spin the first one had. In this case, it's up, so it's up here. And then nitrogen, Hund's rule again. Finally, with oxygen, we start pairing them up. And so this right here is how we write electron configurations, it's just shorthand for where the electrons are on that atom, which is really useful information. So oxygen has 8 electrons. Its electron configuration is 1s2, 2s2, 2p4. Now, in the next module, I'm going to show you how to use the periodic table to read the electron configuration. You don't really have to memorize as much the relative energies of these subshells, these orbitals, because you can read it right from the periodic table. So let's answer a question and we finish with this module. So let's say we have a neutral silicon atom, okay, in the ground state. Well, what do I mean by ground state? It just means that all the electrons are in the lowest energy orbital where they can be. Now, let's say, for example, boron. If I gave it the right amount of energy with probably a laser, I could take, say, one of these electrons or maybe one of these, let's say a 2s electron, and I could excite it up into a 2p orbital, the subshell. That would be an excited state. This, though, is its ground state. Everything's in the lowest energy place that it can be. That's all I'm saying here. Whoops, there's the answer. So we want to know how many unpaired electrons there are in the ground state of silicon. Okay, so see if you can answer that question. So what you do is you just say, okay, silicon has 14 electrons, and the order of the energies of the subshells is 1, s is less than 2s, which is less than 2p. Now, what I'm thinking about at this point, probably it's useful for you guys to go back and look at this right here, this diagram. 1s is less than 2s is less than 2p, less than 3s is less than 3p, is less than 4s is less than 3d, and so on. So 14 electrons, that's the order. Start putting them in, no more than 2 to an orbital. Each box represents an orbital. Each arrow represents an electron, no more than 2. So 1s2, 2s2, 2p2, 4, 6, 3s2, 3p2. And so we can see that Hund's rule tells us that there must be 2 unpaired electrons. And by the way, the electron configuration would be 1s2, 2s2, 2p6, 3s2, 3p2.